então.
Yes, let's start. I think we should do it in English because we have our collaborator from China here today. So okay. So now we are online on YouTube. I think we can start, right? So, so thank you everybody for being here today. Today we have the honor to receive Professor Thiago Rodrigues de Oliveira from the Federal University of Fluminense Federal University. He's going to talk about simple quantum engines, quantum engines, that's right. So, Thiago, thank you very much for the acceptance of our invitation, and you may start whenever you feel ready, okay?
Okay, so thank you for the invitation. I mean, you and Lucas and all you, the group. So it's a pleasure to be here and talk a bit about the work I have been doing. It's also a pleasure. So I will talk about this paper we published last year. And I mean, if you look at the paper, actually the title is different, but I like the previous title. So to comply with the referee, we changed the title, but in the magazine, but in my presentation, I choose the title. So I will keep the title that I like it more, okay? But in the paper, it's a different title, okay? So this is about counteractive properties of a simple quantum engine. So I think the idea of thermodynamics is to find new phenomena when you have quantum systems in thermal engines. And I believe we find something that, as far as I know, it seems to be new and it enters, okay? So, but I mean, I also, I mean, I'm not consider myself expertise in thermodynamics and even not in quantum thermodynamics. So I always happy to talk about this result to know if it's people really think it's counteractive or maybe I'm just missing something. Okay, I think it's probably that can happen. So I just want to say a little bit about my research interest. So I'm usually interested in quantum correlations in many particle systems and collective behavior. This is like quantum correlation phase transition, equilibration, thermalization of quantum systems, isolated quantum systems. Are actually very, very interested in this equilibration thermalization of quantum systems that are isolated. And this is related to the emergence of the second law of thermodynamics, the classical and quantum transitions from principles of quantum mechanics itself without adding any new hypotheses or whatever. Okay, I have also worked on these areas and you can check it out. So I also give a brief introduction, I mean, on the works of the quantum thermodynamics. I'm not sure how many people here are really, I mean, aware of all these things. So I think this area of quantum thermodynamics, it seems it started on this, with this paper on 59, okay, about these guys. They propose that you can understand the three-level masers as a heat engine, okay? So just showing that there is a way to understand the lasing. In this case was a maser, but everything would work for a laser also as a heat engine, okay? And then there is also this work 20 years later of Aliki, which is a well-known guy in open quantum system, when he proposed that if you look at the energy of a system, that you're changing the Hamiltonian, you can divide this difference in energy in two terms, okay? And this first one is due to the change in the populations, and he said that we should call this heat, okay? And this other one, which is changing due to the Hamiltonian, like you're changing the external parameter, you should call it work, okay? So this is the first definition, I would say, of work and heat in thermodynamics in quantum systems, okay? This, in this case, was open quantum systems. And it's the one we still, it's still very popular. Remember, we know there is a lot of discussion right now in the community about how to define work, in quantum systems. But this is still, I mean, the first definition and the one that, as far as I know, is still very used. And then, I mean, this is the paper on 79, and I think like later, in 2004, there was this paper by Kiel, where he just proposed a very simple quantum engine with a single spin, okay? And this paper got very popular, and it seems for me, again, I'm not really aware of all the literature, but it seems for me that it's one of the first papers of the modern age, let's say that way. Okay, and then there is now this paper. I mean, that's starting pouring up many papers. You know, the single atom heat engine, and now these papers are at the beginning. And nowadays, I mean, you have a bunch, hundreds of papers on heat engines alone. I mean, not even talking about the whole area of quantum thermodynamics, where you also have research theories and other things. And I mean, I also want to do a little bit of provocation, because I think quantum thermodynamics actually really started maybe on this paper of Einstein, where, I mean, it's a paper that is not well mentioned, but I mean, it was after the photoelectric effect, is like 1907, when Einstein proposed, you know, a model of a solid which has harmonic oscillators, and he quantized these harmonic oscillators and showed that
it's even worse, Thiago. I would say that quantum mechanics started with thermodynamics, with Planck.
Yeah. You can also,
was starting about a thermal equilibrium that quantum mechanics was born.
Yeah, I mean, even the work of the spectrum of the radiation, the black body radiation, is also quantum thermodynamics. So and that's true. Okay, I like this paper of Einstein, and it's every time people like to say about the first works on quantum mechanics itself, they forgot to mention this paper when they show that the specific heat of a solid can change with the temperature, and this was not possible with the classical theory. And then you have a thermodynamic system where you have a quantum property. So I think that the best thing to nowadays what we have is like quantum stochastic thermodynamics. No, I think this would be a better name, but I don't choose names for the community. So it just, I mean, provocation. So the way I understand this new quantum thermodynamics is the idea is how quantum effects can improve the performance of small thermal engines. Okay, I mean, this is one of the areas. No, as I said, there is people that are more interested in research theory and other things. Okay, so the idea is like if coherence and quantum correlations can improve the performance of some engine. Also, what's the role of quantum fluctuations? We know that this could be important. And also, I think another thing that quantum thermodynamics can be, is the idea to use the language of thermodynamics to understand better the quantum phenomenon. I think this was the first proposal of the Maser in the 57, was this idea. They were showing that you can understand this process of the Maser as an engine. Okay, so using the language of thermodynamics to understand some system that was already well understood, but then maybe you can get some insight given this new language. Okay, and the idea today is very simple. Now is to study a simple engine with the Otto cycle. Now, and I'm gonna show you that we can have increase in the efficiency, which was on a performance of the engine without coherence or correlation. So it's a bit of a drawback because you don't have coherence and correlation. We're always looking for coherence correlations, but you still have increasing efficiency doing some quantum phenomena, but which is not related to correlations. And also I try to show you that there is some counterintuitive properties. Okay, so which is the idea? Now I'm gonna talk a little bit about the Otto cycle. So this is the Otto cycle. There is the cycle you have like in your combustion cars, in the engines of your cars. And the idea is that you have two adiabatic processes, okay, which is the expansion of the gas and the compression of the gas, followed by two isochoric processes where they exchange heat with the baths with a fixed volume. Okay, this is a very simple cycle because here in the adiabatic you just have work, and here you just have heat. So you can separate the four strokes in the strokes that only involve heat and only involve work, and then this makes things very easy. Okay. And if you do a entropy volume diagram, which I'm going to use, it's a very simple diagram. The adiabatic is just constant entropy. And you can see that it rotates in the clockwise direction as engine. This is important. You know that this cycle, the direction of the cycle dictates if you have an engine or a refrigerator. Okay. And in this ideal gas Otto cycle, you can show that the efficiency is only related to the first from the two volumes, actually, So is the one, there's this ratio here between these two volumes. This gamma is related to the adiabatic, when you make a diabatic process in your gas, you have these constants, which is related to the specific heat, the ratio between the specific heats of this gas. But what I want to say is that doesn't only depend on the compression ratio here, okay? And you can show also easily if I plot the temperature of the hot bath and the cold bath, you can show which are the regimes that this guy operates as an engine. So this T3 here is the temperature of the hot bath. And of course, you need the hot bath hotter than the cold bath. And if you start to decrease the temperature of this cold bath, at some point you don't have an engine anymore. You start to work as a refrigerator. And later, if you even decrease it more, you start to work as an accelerator, okay? And the accelerator is just a way that you put work in our system and the energy just goes from there is heat going from the hot to the cold bath, which is the usual way. We don't need to do anything. No? It's the natural flux of heat from the second law. But you put work and then you just increase this ratio where the heat is going from one to the other reservoir. And from this simple system, you can find the conditions for this to happen, okay? And this is going to be very important, okay? You should be, I mean, this is even a textbook exercise that if you get an engine and you exchange the baths, you put the cold bath and the hot bath, you change the positions they are in the cycle, usually you get an accelerator, okay? You don't even get a refrigerator. And this means that if you have an engine rotating on this direction in your cycle and you change this direction, you can get a refrigerator or accelerator, okay? And also you can see this because the change of the sign of the work will change, okay? Because the sign of the work depends on the direction you are running your cycle in these diagrams, okay? Any questions? Okay. So the idea is that I'm going to do a Otto cycle, but now it's a magnetic system. It's a single spin. The first one that was studied by Kiel in 2004. Okay. Now instead of varying the volume, I'm varying the magnetic field. I have a spin in a magnetic field, and the pressure, instead of having a pressure, the system has a magnetization. Okay, it will depend on the magnetic field. So if I have a single spin, there is actually no new physics. No, you can now show that the efficiency is also the ratio between the two fields. You have a beginning, you start with some field and then you increase it and then you decrease. Here I am the diagram of this guy again, okay? And there is no new physics in the sense that the efficiency is the same, okay? And the conditions to have an engine, a refrigerator, accelerator is the same, okay? And now I'm just plotting here this diagram of the cycle, okay? There is some things here like the engine now, it rotates in the counterclockwise direction, okay? It's different from when I have ideal gas, and this guy is the accelerator, okay? So the main message is that everything is the same. You just change volume to magnetic field, pressure to magnetization, and nothing else happens, okay? So the idea here is to study what happens if I have two spins, okay? And actually, I should also say, no, this is the same thing if I have one spin or two spins or 10 to 23 spins that are uncoupled, okay? The calculations are all the same, okay? If you're not talking about fluctuations, it doesn't matter how many spins I have as far as they're not coupled, okay? But the idea here is to start two spins and get some coupling. I'm gonna couple these two spins. So this would be the Hamiltonian without the coupling. I'm just gonna couple these two spins. And I know when I couple these two spins, I can have quantum correlations due to this couple and see the role of this couple and these quantum correlations and the operation of the engine, okay? I also add some constant here just to make the angular values easier. There is now my angular values here are 4 now, and I just made one of them 0, just make calculations easier. I just added a constant here. So, and here I can have two regimes, okay? These are the eigenvalues. You can see that two of them depend on the field, and one of them depend on the coupling, okay? And now I'm going to define two regimes. One is what we call the strong coupling, where this eigenvalue is the eigenstate, okay? And the other one is the weak coupling when this guy is not the eigenstate. It's not the ground state of your system, okay? And also it's important that the eigenstates, no, these are eigenvalues, no? In the eigenstate, they don't depend on the H or the J, okay? It's gonna be important also because I mean, I would say that, I mean, the adiabatic approximation actually is exact here, okay? Because the eigenstate, they don't change when I change the Hamiltonian. Okay, so this is the system. I'm just going to study the Otto cycle and the very idealized Otto cycle, and I have full adiabatic, complete adiabatic, full thermalization, and all this. So the quantum adiabatic here is that I'm going to just change the magnetic field. So you can imagine that you have a magnetic field, and you just change the distance between them, and then you change the value of the field here, and this makes the adiabatic process. And here it's also important to say that what I'm doing is not a thermodynamic adiabatic, but it's a quantum adiabatic, okay? In the sense that I wanted to change the Hamiltonian, so I change the eigenvalues, but I don't change the populations. So this is the idea of a quantum adiabatic process, that you change it very, very, very slow, that the population, so you don't create excitations in your systems, okay? In this case. So so I'm just doing this slow change, okay? And I should mention that this is usually not equivalent to the thermodynamic adiabatic. I'm going to talk a little bit more about this. And also, actually, we realized it afterwards, no, that actually here, as the eigenstates, they don't change with the parameters of Hamiltonian, this change doesn't have to be slow, okay? Theoretically, if the system is really isolated, it doesn't have to be slow. You can even have level crossings, okay? Because the eigenstates, they're not changing, okay? The eigenvalues are, but the eigenstates are not changing. And the eigenstates is what matters. Okay, and so here, I'm just saying again that I start with the thermal equilibrium, I do this quantum adiabatic, okay? For sure, there is no entropy involved, okay, because it's a unitary process. But as I keep the populations constant, change the Hamiltonian, okay, the ratio between the populations here now, they don't obey what you would expect from a Gibbs state for the new Hamiltonian, okay? So your final state is not in a thermal equilibrium anymore, okay?
So there must be thermodynamic entropy production there, because you start with a thermal equilibrium and take out the system out of equilibrium. This implies thermodynamic generation, thermodynamic entropy creation.
Yeah. No, I agree.
I agree with you that von Neumann entropy doesn't change because it's unitary process, but thermodynamic one does. And this is because you have to create coherences between the energy and gain levels, otherwise you cannot change the populations and you cannot take the system out of equilibrium.
Yeah, I completely agree. So I think there is some kind of production of entropy here. So that's we go in a territory that should be explored, no? Because when you go out of equilibrium, then all your von Neumann entropy is not equivalent to the thermodynamic entropy anymore.
Exactly.
Now, I mean, the question is how can I still define some kind of thermodynamic entropy in this no equilibrium system? So this is a question I think it's very important. I didn't have time to think much about it. And I think, there is some people that already in the classical regime try to talk about entropy in out of equilibrium systems. No, there
are even for quantum systems, for instance, there are old papers. Yeah, there are old papers by Anatoly Polkovnikov.
Diagonal entropy.
And with not diagonal entropy, but he associated entropy in closed systems with the generation of coherences.
Okay. Yeah, I should look at. I think it's important to look at these things with more care. I haven't done it yet, and I haven't seen people talking about it much. At least in this paper of quantum engines, which are the ones that are really for. I haven't seen anything about this. Huh? This is just ignorant in most of the works I haven't seen. But it's an interest point that we should try to look at. And of course, what happens is that I should also say, if you just have two systems, then you can still define effective thermal state here. And also, if all your levels have the same distance, like in the harmonic oscillator, you can always also define some effective thermal state here. But this is very specific situations. And we also see that many people work on only on these situations, and that's why they ignore these things. Okay, any other questions? Okay, so this is the quantum adiabatic process that we're gonna do in your Otto cycle. And okay, and then this is the quantum isotropic one. When I put the system in contact with the bath, I fix the Hamiltonian and let it exchange heat. Okay, and how it happens is that the levels doesn't change, but the populations change. Okay, this is, I mean, this one will decrease, that one will increase. Okay, and between here anything can happen. Okay, in the SH diagram, that's what happens. Okay, and I should also point out that here, when I change the adiabatic, these two levels, they depend on age, they change. But this level, which is the one depending on J, it doesn't change when I make the adiabatic process. Okay, it's like a isolated level. He's not coupling with the magnetic field, and that's going to be very, very important. Okay, so the idea is, of course, I mean, this model of, I mean, the single spin was studied in 2004. Okay, and the coupled spin was being studied before in 2007 already, and there are like many papers we studied this model of two coupled spins with the Otto cycle, and it's an ideal Otto cycle, and I have the perfect adiabatic, perfect thermalization, and they're like, I mean, a lot of paper. I'm just citing two of them here, and the main of, I mean, most of this paper, they are trying to relate an increase in the efficiency. So I change the J, the coupling, I see an increase in the efficiency, and then I see that there is an increase in the correlations, and they try to connect these two things. So say, oh, see, increase in J, you increase the efficiency, but you also increase the quantum correlations, maybe entanglement score, whatever. So there is a connection between these, but it's actually, it's not really, you can't really find a true connection in all the regimes of operations. It's just in very, very special cases that you see that the two ones goes together. The increase in the efficiency and in the correlations are the same. Usually they are not, okay? So people try to establish this, but it was not, didn't get anything conclusive and very general, okay? And also in this paper here, which I think very well done and writing, this paper here, they showed that the efficiency of our system over the efficiency of the Otto cycle without coupling, with at a zero, is given by this relation. Okay, there is an AJ here, so they prove this relation. Okay, but there is no physical interpretation. No? I mean, can you give a physical interpretation what the efficiency is increasing from this? And I think the main contribution we have here is given a physical interpretation. Okay, it's more on the conceptual side than in calculations. Okay, so I should acknowledge all these people. You know, I mean, they already was studying the system, doing a lot of correlations, but I think there was, I mean, they missed some physical interpretation. So here it comes their first physical interpretation. If you look at the heat exchange between the baths, you can write it. No, the heat is due to the change of population. So you can write it as this level, the level that depends on J, and the change in population there, and then the other level depends on the fields, and the 4 level with 0, there is no heat being exchanged there. The same thing for the other bath, okay? And the work is the sum of these two things, okay? First thing you should see is that when you are going to do the work, this term here cancels out and doesn't appear. And that's what should happen, no? Because the work is due to the change in the energy level, not on the populations, and the level that depends on the coupling, this level doesn't change, okay? So the idea here is to try to understand, to interpret this exchange of heat between levels as happen between each level. It's like you can think that as each level is a degree of freedom that allows you to exchange energy or heat, okay, between the system and the level. As in the gas, you have many particles. Each atom is exchange heat with the bath, and you look at the total thing, okay? But here, not talking about particles, but about level, energy level, okay? For me, it remembers like some second quantization idea, okay? And now I have this idea, I have the hot bath, I have the cold bath, I have my system here, and I have one level, which is the J, I'm calling level 1, and I have level 2 and 4, which are here, okay? And then you can see that this expression here, what he says, it says that to have increase in efficiency, here, this term should be negative, okay? But what is this term? This heat here is the heat that is coming from the hot bath. This has to be positive to have engine. But this is the amount of heat that is flowing through this level. And to have increase in efficiency, this guy has to be negative. So this means that through this level, in this physical picture I'm proposing, through this level, the heat is going in the opposite direction that we expect, okay? Of course, the total heat is still going from the hot to the cold, but this level, no, the energy is going this. So this allows you to have the same work output, but with less heat coming to the system. And this which allows you to have increased efficiency. So the coupling of the spins allows you to have increased efficiency, but it's not related to the quantum correlations between this guy, but it's related to the structure of the energy levels that you have. That's the main measure. I mean, this is one of the main results of the paper. As I said, it's just an interpretation of the math that was already there, okay? And allows you to understand, okay? I can just have like one single spin with many levels, like spin 1, 3 halves, whatever, and maybe these guys this mechanism could be at work, okay? And I could still try to engineer some energy level structure to allow for this mechanism.
Thiago, can this be related with fluctuations?
Yeah.
Because
so,
my question is this, because I mean, the second law states that the heat should flow from the hot bath to the cold bath only on average.
Yeah.
So sometimes we can observe the opposite flow.
Yeah. So here, I mean, this work is very limited, I would say, because we don't take into account fluctuation. We're just ignoring the fluctuations. You're just talking about average quantities. So I think when you go to fluctuations, it can happen that the total heat sometimes can go from the cold to the hot, okay? You could have a statistical violation of the second law because it's a bit different because here we are just assuming that the total heat is always from the hot, from the cold, but is that part of it that is flowing through this, and it's an interpretation. I mean, some people can claim it doesn't make sense to separate these two terms, okay? And I think it's like, I mean, when you have a cup of tea, okay, you have molecules. I mean, one way that this guy loses heat is that some of the molecules that are in the surface of your coffee, you just get out to that atmosphere, okay? And this is the way you lose heat. But sometimes this coffee also gets some molecules from the air. It also happens. So you also have, your coffee is also getting some microscopic heat, but on average, the heat is going out from your coffee to the air. Okay, I think this is the... So this is the first result of the paper. I mean, of course, at first I really like it. Sometimes I'm not sure, I mean, how general this can be, which kind of systems. I mean, in the paper, we did try to expand this for sometimes when the system is not totally uncoupled. Okay, there is a small coupling from our general system. There is a lot of discussion in the appendix about this. So second result, okay, is not related to the efficient, but is related to the regimes of operation. Now I'm still, again, showing this kind of phase diagram where it shows where the happens, I see that now first, I have a new regime of operator that we call a heater, okay? I didn't propose this name, I got it from a paper from Michele Campisi, and this heater is the one when you put work in your system, and this energy goes to heat to both reservoirs, to both baths, okay? So that both the hot and the cold bath are getting energy that was put as heat in our system. And you see that now on this border between engine and refrigerator, you can have an accelerator and you can also have a heater, okay? This is for a small coupling, okay, this guy. So I'm just studying. And actually, unfortunately, you cannot get analytic expression for this from these lines here, where there is the border between this region, okay? You cannot solve analytically this expression. And now what happens if I really increase your J? Now I'm the strong limit. The J becomes the ground state, okay? What happens is that first, now this area here, it becomes an island, okay? You see there is, even if you decrease your cold bath temperature to 0, okay? You don't have an engine anymore, okay? You don't have an engine anymore. And also something else happens in the other side, okay? And this is what I call counterintuitive properties. So let's see what's we doing. So the idea is that the engine can operate in the reverse direction, okay? Let's just me come back here, no? Here I have an engine. If I go to this side, I start to run the cycle in the opposite direction. And now I have accelerator, okay? And this, I think, what we expect usually with basic systems that we study in thermodynamics, okay? But what I'm saying for you is that even in this region where I'm operating on this direction of the cycle, where work should be negative, it can happen that it is positive. So I can now exchange the bath's role in your cycle and still have an engine. I mean, in my very naive understanding of thermodynamics, and I'm being serious here, it is very naive. I don't have a very understanding and the literature of quantum engine, or not even on classical engines, okay? I never expect this. For me, this is very counterintuitive, okay? That you can exchange the whole of the baths and you still have an engine operating, okay? You can understand this physically in the sense that what happens here is that you get the cold bath. First thing, the J level now is the ground state, okay? And energy, work cannot be exchanged. All the heat that is going through this level cannot be converted in heat. No, this picture that I was showing here, no, it also has this, only the energy, the heat that is going through this level can be converted to heat. The energy that is going here, it cannot be converted to heat. And if this level is the ground state, and you make the cold bath very, very, very cold, most of the energy is just flowing through that level, and it cannot be converted to work. So you can make the work that is necessary, you know, like the work you input in the engine, much smaller than the work that you output from it, due to this guy being the ground state, and you still have an engine operating here, okay? So there is a way to see that this makes sense, but I still think it's counterintuitive somehow. So this is the second main result of the paper, at least from, I mean, the one I like it. And there is also this other result, which I also think it's counterintuitive, because, I mean, I have this intuition also, that if you have an engine and you make the hot bath very hot, or the cold bath very cold, you're always gonna increase the efficiency somehow, okay? This is a way now that you make your engine work better, is to increase the energy of the temperature and the energy of the hot bath and decrease of the cold bath. And you see that the Carnot limit, you know, goes to 1 when you do this, okay? So I would expect actually, no, that if you have a cold bath that operates in the limit of 0 temperature, you can achieve the maximal efficiency somehow, at least if you're in the Carnot cycle, okay? But what happens here actually that you decrease, imagine you start at some point here inside this island, and then you start to decrease the temperature of the cold bath. You believe that this thing, the engine is getting better. No, you are refrigerating better your engine. No? It should operate better. But at some point, it just stops to operate as an engine. Okay. This, again, for my naive intuition, it's strange. It's counterintuitive. Okay. But you can still understand what is happening in terms that the J level is the ground state and is getting all the flux of heat and is not able to convert and heat and work anymore. So this is the second counterintuitive property of the engine, okay? And now, I mean, I don't want to go through all the details. In this regime of operation, also it happens that if you increase the temperature of what would be the hot bath here, it's also stop to work, okay? There is a maximum here, okay? And also, I mean, this, I don't think this is, I have no intuition actually at all about this, but if you go to really strong coupling, like I was working here with J.7, it's already the ground state, but it's very close to the other levels. But if you make the ground state really deep, okay, actually the refrigerator and the heat, the region where you have a refrigerator and the heat just vanishes, okay? I haven't explored this much also because I don't have any intuition what should happen here. And also, coming back to the efficiency, no, I also have this intuition, as I was saying, if I increase the temperature difference between the baths, my intuition is that the engine should operate better, okay? And actually, you see this now. If you see this curve, here you should pay attention that I'm plotting beta, not a temperature anymore, okay? And this is the engine operating the usual direction, in the upper part of our diagram, in this region here, no? Operating this region. I can see, no, that if I increase the temperature, I decrease the temperature of the hot bath, which is increasing beta, is decreasing the temperature of the hot bath. What happens usually is that the efficiency decreases. Look at this blue line. This is what happens most of the time. Your efficiency decrease. This is my expectation. But if I go to very low temperature of the cold bath now is very, very low, okay? And I decrease the temperature of the hot bath, so the difference is decreasing, it can change. The efficiency now doesn't decrease, it can increase first. At some point, it's gonna start to decrease because at some point you don't have an engine anymore, it has to go to 0. But you can increase it. So this is another way to increase the efficiency of engine. Here is the efficiency of the engine without coupling, the dashed line. So you can again engineer with your coupling and the temperature of the bath an increase in the efficiency. Note that when you don't have coupling, the efficiency doesn't depend on the temperature. It just depends on the ratio between the two fields or the two volumes. But of course, in this case, now you see the increase in the efficiency, but here I'm plotting the work output and it decreases exponentially. Okay, so you can have an engine operating almost close to 1 efficiency, but with exponentially small work output. Okay, and I'm not talking about power here. Okay, there is no power here because in principle you operate in the adiabatic limit, and in this idealization actually doesn't have to be very slow, but I'm not talking about power because usually we have this idea that if the efficiency go to 1, the power should go to 0. But I'm not talking about power, just talking about the work output. Okay. And also when I have the engine operating in the other regime, which is rotating in the opposite direction, the same thing can happen. Okay. Now I can increase, I can decrease the temperature of the hot bed again, and I still can see an increase in the efficiency, okay, the beginning. It's a very, very small region. It seems you need fine tuning to do this, but maybe it's possible you can increase this efficiency. And you still have, and what's interesting is that the work can still be finite. Okay, it doesn't, on this region here, the work is still finite. So it seems that maybe operating this engine in the opposite direction, it can be better. You can have a good efficiency with a lot of, with a reasonable amount of work output. Okay. So finally, I'm being very fast. Does anyone have any question? I think I'm coming to the end and still have plenty of time. Plenty? No, but I still have some time. Okay, we can discuss as much as you like in the end. So, and now I'm just resuming the physical interpretation that
I think that's Norton raised the hand.
Oh, okay, sorry. Go ahead, Norton. Should I do anything? No, to allow someone to talk.
I don't think so.
Yeah.
Who is?
Norton, we can hear you.
Yeah, we can't hear you, Norton. You are talking, but we can't hear you.
Yes.
Yeah, I see that.
Okay, so yeah, maybe he's facing some audio issues, so I think we can continue,
okay,
and
let's
maybe
keep on, and
we can ask his questions at the end. Okay.
Yeah, sure. So, and so finally, the physical interpretation that we are proposing here, is like to consider this each level as the heat actually flowing through each level. And this is the usual engine with no coupling. Both levels are exchanging energy in the right direction. Okay, let's see this. To have an efficiency gain, this level, the heat has to go in the opposite direction. And also, we showed, we can show that when the engine is running in the reverse direction, okay, what is happened is that is the inverse of here. Now the heat through this level, most of the heat is going through this level and is not becoming work. And the heat and is going the right direction because now I have the hot here. Okay, I changed the roles of the baths. And this level, which is the one when I can have energy going through, becoming work, is going on the opposite direction. And also I have the accelerator, also the one that's upper there, where it is going also in this. So this is a resume of all this stuff. So just idea that it's possible to understand what is going in terms of energy levels and in the term of the structure of the energy levels. So to conclude, so we have propose a new, people don't like, I don't like when people talk new, but I use it with here, a new mechanism for efficiency increase, which depends on the level structure and the fact that some levels doesn't couple with the external parameter. So I'm changing the field and there is some levels that doesn't change, okay? You can generalize it you can have many levels that doesn't couple, you can have just one as here, okay? And the idea is that doesn't involve coherence or quantum correlation. It's just the structure of the energy levels. It's still quantum, okay? It's just not involve quantum correlation. And then we can show that also you can have counterintuitive properties, okay? An engine that can rotate in both directions of the cycle, efficient that increase even when the temperature of the difference of the different bath decrease, and also the engine may cease to operate if the hot bath becomes too hot or the colder bath becomes too cold. Okay, I should also say just two final things is that this was the first work we done, which was in the adiabatic limit. But you also have this another work with the Cleverson, with a postdoc here, where we did all the calculations, consider now a system where the eigenvectors depend on the external parameters, and now you need to take care of the time to do the adiabatic, and we studied how the time changed these things. And the idea was all these properties that were showing, these counterintuitive properties and this thing of the efficiency gain, will they survive when I can have excitations? My diabatic is not perfect anymore. And we showed in this article, which actually, I mean, it's an archive and was accepted this week to Physical Review E. We show that this also happens when you don't have the perfect diabetic, okay? And also, I mean, I really truly saying that, I mean, for me, this is counterintuitive, but I mean, I'm really happy to know of other systems where these things happens, and maybe this is very well known for people who study thermal engines for, I mean, know of more complex thermal engines. This is already well known, and that's why, I mean, that's why for me it's counterintuitive, okay? So I really would like to know about other works that show this. Actually, I also have been working on trying, because it's not clear that this, you need really a quantum system to have this change this properties here, no? So I actually doing some calculations with classical spin systems and trying to show if these things could also happen there, okay? This is work that is in progress yet. So I think this is it. I mean, I like to be brief because more time for discussion, it's more funny. So thank you all for your time.
Okay, so thank you, Thiago. And now, do we have questions?
And be free to, I mean, even for the students, no, ask any kind of questions. I mean,
well, while the students are thinking about this, I have one actually. I have several actually.
Please.
First of all, can you please show us the Hamiltonian again?
Yeah. Here.
Yeah. Because this thing happens in the strong coupling limit. I mean, this.
Yeah.
This effect that is called counterintuitive. So my first question is, until what extent we can consider this Hamiltonian a valid one for strong coupling? I mean, because you are considering only linear response.
Yeah. I mean, so yeah, I should be warm because I mean this terminology is a bit strong coupling can be a bit misleading. Okay, here you can solve everything exactly. So it's not strong in the sense of doing perturbation theory because everything is just a two-level system. I mean, actually, this Hamiltonian is the Heisenberg isotropic Hamiltonian. So the couplings are the same in all the directions. You can even for many spins, you can solve it analytically. And here is just two spins, you can easily solve it. So in this sense, strong is just a way to say that this is the ground state. It doesn't involve anything of approximations that we are doing.
Oh, then I missed the mechanism behind the fact that when you decrease the gradient temperature, I mean the difference between the temperatures of the hot and cold bath.
Yeah, the question is
why do we have an increase in efficiency?
No, oh, okay. So, okay. Actually, that's something I don't completely understand in terms of the energy levels. I mean, so that's behavior. That behavior that you change the temperature. Okay, here. No, I mean, so I can't explain why these guys are why you don't have engine here. I can't explain why you can have engine here, but it's a good question. I haven't really touched much about why this increase here. How can you understand it? This is a good question. I haven't really looked at some point.
I mean,
we try. I really look at a lot about how the populations are changing during this change of the temperature, but it's because I mean it could happen. So this is interesting. No? When I do this thing,
I mean this should be related with some kind of decreasing entropy. Because efficiency and entropy are fundamentally linked.
Yeah, you can.
So if you increase efficiency, you have to decrease the entropy generated in the universe. Otherwise,
No, good. Yeah, yeah. Actually, I mean, this is what also we have discussed at some point. It would be nice to try to understand this phenomena in terms of when I do the coupling, what changes in the cycle in terms of the entropy exchange with the paths, and also, so I think one thing is trying to understand this in terms of the entropy change with the baths. Maybe something has happened there with this entropy, but I think even more interest would be to understand what has happened with the entropy, because you're doing it, the thing about you're doing the quantum adiabatic, but you're not doing the thermodynamics. So you're getting out of the equilibrium. As you said, maybe you're probably producing some kind of thermodynamic entropy there, okay, which there is no consensus how to define. And looking at this thing maybe can give some idea also. Yeah, I agree with this. And another thing I should say that I tried to understand this in terms of what happens with the level populations when you couple to the bath. And this is what you know is that the lowest level, when you couple like with a cold bath, this guy should decrease and this guy should increase. Okay, this has to be, no, this has to be. The ground state, the population always decrease, and the highest one, it increases. But what happens between the populations in the middle, it doesn't, I mean, it can happen a lot of things. So I know that something weird happens with these populations that are in the middle when you have these counterintuitive properties. I don't remember if this behavior of the efficiency increase also show this, but I know. So I worked a lot trying to understand all these things in terms of this, what has happened with the levels, but I didn't really get a clear picture at the end. So that's why we stopped with that. But maybe it's also some way, yeah. But but this is related to the exchange of the energy heat with the back. I think something in the adiabatic that creating entropy also may be fundamental and a different way to understand this. Yeah.
Oh, I think that this is something inside the system and has nothing to do with the bath. I mean, I just put a paper in the chat that discuss the generation of heat due to coherences. And
good. I mean, that's a good thing out there.
And he defined, and the guy defined the heat exactly as the generation of coherences when you have transitions between energy eigenlevels.
So this is the work you have with the guy from.
No. This is much older. The work that I have with the polishing guy, we just put these sort of things into a mathematical solid ground.
Okay. I don't know how I see the chat right now. Let me see.
Can you hear me now? Can you hear me?
Yes. No, we can hear you.
Thiago, first of all, thank you for your nice talk. I have a question, but it seems to me that Lucas have another one. Lucas.
No. Okay. I mean, we can discuss. Please go forward.
Okay. Thiago, I suspect that the correlations are taking a play in this process. How can you be sure that correlations are not important, or correlations aren't present in your system, and this correlation possibly is related to work? How do you see this?
Okay. So just sorry, who is talking is Norton. Okay, Norton. Okay. Yeah. Okay. So my claim that correlations are not. So there are two things. First, I think if you plot the increase like in the entanglement or the coherence in the system, you plot it with J, and then you say the same plot of the increase in the efficiency, you see that sometimes the efficiency increase and the correlations are decreasing. So it doesn't seem to be, you always have a monotonic relation between increasing the efficiency. And so this is, most of all these papers, they were looking for this, and they never found a monotonic behavior between this. But I'm not saying, yeah, but I should say, I mean, of course, correlations are important. You should have correlations to have this structure. So I think I'm saying that I think it's easier to understand and it's a more clear picture when you look at this structure of an energy level. But I mean, the fact that this guy doesn't couple with the rest, maybe he's related. I mean, of course, correlations are necessary for this, but in this sense, they are relevant, but it doesn't seem that it's a clear picture between them. That's why I'm claiming it.
I get it.
And also because I couldn't think, I could imagine that I have a single system where there is no two parts, which this kind of energy level. No, I mean, I haven't thought about this, but I don't see why not. I could just have a single system, okay? Like I was saying, a spin with greater than half or something else, where I have this energy structure, and then I don't have anything about correlations there anymore. Yeah.
Okay. May I have another question?
Sure, I mean, as much as you.
Thank you very much. My question is, I think when heat is pumping inside or into the system, there is a problem in quantifying how much work, how much heat is going from or out to the system. So in the calculus of this efficiency, have you taken this into account? I'm not sure if I expressed myself clearly.
So I'm not sure. Also, if let's say, I mean, this is a very simple model because we're really first in the Otto cycle you have this advantage that heat only happens when they're coupled with the baths. Okay. Second, we are considered. I mean, the most idealized model of thermalization, where just consider that you have a perfect bath, you couple, and you get your thermal system. So you are just consider that the guy will completely thermalize with the same temperature of the bath. And I think in this scenario, heat is well defined. When you have the Otto cycle, yes, and have a perfect bath, I think the exchange of heat is well defined. But it's true that in other not so idealized models, then it's a problem. Is that your point, or I mean?
Yes. And, for example, calculating the work, some energy can be stored in the correlations. So when you calculate the efficiency, I'm not sure if this was taken into account since you are neglecting correlations.
No. I mean, I'm not neglecting correlations. I mean, I'm really solving the full model, so that there is correlations between them. There are correlations, and I mean, so I'm not neglecting that at all. Okay, so and in the case of work, I also think that here, I mean, in the case, I also believe it's well defined, and I'm using the most basic definition that the work is the expectation value of the energy, is the difference between the expectation value of the energy in the beginning and at the end of the adiabatic. And I'm considering that the system is completely isolated, so there is no heat. So all this energy that being exchanged during the adiabatic, I'm calling it work. Okay. And
okay. Yeah, Thiago, but I'm concerned about some energy that could be stored in the correlations, and so this this should be taken into account somehow.
I mean, yeah, but I don't know how to separate. Okay, so I don't know how to separate. So I don't know. Actually, maybe one direction. I mean, these people on this paper, this Thomas, they try to understand something. I don't completely agree, but they have this picture. They call it the local work. So what they do, I don't know if that's what they do, is that they get just this part. So to find the energy in the system, I have to make the trace of the Hamiltonian and the density matrix of our system. And what they do is that they consider what they call the local work or the local energy, which is making the expectation value of the state of our system, the density matrix, were just with this part of the Hamiltonian, and they call it local work. Okay, and then you can say that you can also make this expectation value with just this part of the Hamiltonian, and this saying that this is the energy that is stored in the correlations. And I completely agree with this. Okay, I'm not sure about if it makes sense.
But this doesn't hold. Yeah, but this doesn't hold for strong coupling.
Yeah, no, but I mean, it's going to be, again, I mean, I'm not sure about how to divide this. And I mean, but my point, maybe just to answer not, I mean, in my case, I'm consider everything. I'm not trying to separate the energy from what is doing to this term of the Hamiltonian and that one. I'm getting everything together. So my picture is more about not in the terms, that's what I say, no, the terms of which energy is in each this particle view, which energy is in each particle and which energies are it's in the coupling between them. I'm more looking about in terms of energy levels. I'm forgetting about the spins. I'm just looking, that's how I say it looks like, it remembers like a second quantization idea, but I forget about who is who in terms of particles and just look at the energy in the energy levels. But I don't think I'm missing the work that the energy is here, because when I make the trace to calculate the energy, that the change in the energy doing the adiabatic process, I'm taking into account everything. I'm just making a different separation. I agreed with you that I can try to work in another different way and try to separate which is the part that is in this each spin, which part is in the coupling. But I'm not doing this. I'm just separating which is part is through this level and which part is that level.
I see, I see. I have a last question, Thiago. Sorry to bother you.
I'm pleased to answer questions. So.
Thank you, thank you. My question is, maybe, I'm not sure, I'm just thinking about this. Maybe the work as you put in our video here, maybe this work is overestimated because some work was stored in the correlation. This is my point.
I mean, as I said, I mean, imagine, I mean, what I'm doing here, you know, like you can imagine a magnetic field or a piston, okay? I'm just compressing the piston. And now I'm gonna have a gas which the particles are interacting, okay? I have a gas that the particles are interacting. And now I'm compressing the system. And the system is isolated. What I'm counting the work I'm doing on the system. I'm just using, I get the initial energy of the system. And to do that, I get the trace of rho and age with everything, taking into account the correlations between the particles and the gas. I get the energy of the full gas inside the piston. That's the initial energy. Then I compress this guy and I look, what's the final energy? Taking into account everything, the correlations. And I'm saying, as the system is isolated, this difference in energy is work. So I don't think that I overestimate or not this. I mean, I think this is a good definition in the work of this. I agree with you that may be interesting to separate this to the energy that is due to the single particles in the kinetic energy of every particle and the work that is doing to the interactions between the particles and the gas. I agree that this may be a way to see the system and can give you some insight. I think that's a nice thing to do, but I don't think that the quantitativity will change. The amount of work will not change if I'm separating this or not, because here I really consider everything.
Mm-hmm, mm-hmm. Thank you very much.
But yeah, we can also talk more about this. I mean, I think this idea. So I also should say that I look at a lot for literature of engine with a gas that is not a perfect gas, because I mean my idea is maybe this behavior here comes just from the coupling and can be a classical behavior. Maybe I have an idea. I have a gas, classical gas, where there is coupling, and something can happen. So I look at the literature. I just find one paper, which is actually in the European Journal of Physics, which is like a more like the American Journal of Physics. No, it's not really new research. And they find some different behaviors there, okay? Because now you don't have your ideal gas equation, okay? But they didn't find anything like this, that there was an engine operator in the opposite direction. But I think it's just doing to the coupling, it could be classical way. And I think that maybe also trying to understand separating these two works in heat. It's something that these people, they try to understand some of these results here in terms of this local work, okay, local energy. But then I think that it's something maybe what Lucas was saying, you know, I mean, when I have a very strong coupling, does it make sense to separate this energy? And I always like to give this also this idea. Now, if I have two masses, okay, and I have an energy there, it's a gravitational energy. Usually, when I have a energy, I mean, I have anything here on the Earth. No, I have this guy. I say, oh, which is the potential energy of this? And I go there and calculate, and I say, this potential energy is here. If I let this guy drop, this potential energy will become kinetic energy. But that's not completely true, I mean, because the energy is in the system, bottle plus Earth. But as the Earth is very, very big, we forgot about it, okay? So I think it's something here also. I mean, I think if the coupling is small, maybe it makes sense to say that the energy is in the system or not. But if you go to the limit of strong coupling, I'm not pretty sure that making this, trying to separate energy in local parts makes sense anymore. I think the energy is in the system, okay? But it's something I haven't explored, I mean, much. But
yes.
And I'm not sure my analogy is perfect. Yeah, I mean, no analogy is perfect. I'm not sure my is good one.
So questions, Lucas?
Okay, I have one. Based on this discussion, Thiago, something came into my mind. Is this thing related with some sort of decoherency-free subspaces? Maybe because, why I'm asking this, because when we have the coherency-free subspace, we have a clear change in the entropy production. Because the way that BEF acts on the system will not produce entropy, because, I mean, it's free for the coherency. And the coupling that you have there does generate the coherence-free subspaces.
Yeah, I'm not sure. I mean, because yeah, you mean when I have coupling with the BEF? No, because I mean that's what.
No, coupling between, yeah, you have internal coupling and coupling with the BEF. We can have the coherency-free subspaces even for a single spin coupled to the BEF.
Yeah.
So maybe this effect is related with the coherency-free subspaces that makes your heat flow in specific directions, and the entropy production changes because of these guys, because of the existence of these subspaces.
But then you're gonna need to make a model of the I mean, I don't have a real model of the BEF to do the thermalization and see how.
Oh, it doesn't matter. Although the BEF doesn't matter actually. What matters is I mean, I'm assuming that you just consider a thermal equilibrium Gibbs BEF. Weak coupling.
Yeah,
so
I mean,
this is everything that matters. And then you have the internal structure of the system that gives you the coherency-free subspaces. And maybe these guys are related.
Yeah, maybe. I mean, I just don't see much. I mean, the point is, I mean, to understand this, I think in the way you're saying, you really need to couple. I mean, because for me, the coherent free subspace, the fact that I would couple this guy with the BEF, let it evolve, and some of the coherence would be projected because of symmetries and the coupling between the BEF and the system. But here, I'm really not. But here, there are two things. Now, first, I mean, actually, at the end of the adiabatic process, I don't have any coherence. No, in this model here, no. Afterwards, we did this next work. I mean, the work I said showed in the end. There, we consider that in the adiabatic, the process is not adiabatic, and you create coherence. Okay, So here, you don't have coherence. So I'm not sure. I know I talked about coherence, but actually there is no coherence in the total basis, in the base of energy basis here. But I agree with you that maybe in the other model that there is coherence, maybe there is a relation between
I'm not actually talking about coherency. I'm thinking about heat, actually, because maybe the coherency-free subspace impose some limit on the heat flow. Because I'm thinking about entropy production.
Yeah. Yeah, I mean, I think it maybe have a connection. Yeah, I agree, and I agree more strongly that entropy. It's interest. We should look at entropy production here. Yeah, it's just that I mean, as I will look at the chat afterwards because I can't see it right now. But I mean, I think it's important. If I have, I would like to invest some time to try to understand how to define an entropy on these no equilibrium systems. And I know there is not a single one. There is no consensus, but I think it would be nice to get some of these proposals and look at what happened here with this entropy production. Yeah. I think.
Okay, many thanks.
Yeah, I think this could bring us some insight. Yeah, in the problem for sure.
Okay, so I think we don't have questions. No questions on YouTube also. Okay, so thank you very much, Thiago, for the acceptance. It was a nice seminar, so thank you very much. And so see you guys again on 2 weeks, and thank you very much. Okay.
Okay, thank you guys for having me. And,
thank you, Thiago.